A couple other shortcuts. What if we had x raised to the a, and then that was kind of its own, like, entity. And then we raised that to another exponent. A and b could be the same, so it would be x to the a, but this does work if they are different. This shortcut is x to the a times b. So a power to a power, you multiply the powers. Let's prove it. We know that x to the a is a bunch of x's raised to the b. And just for clarification, there's that many x's there. Well, this is the same thing as saying I have... Can I copy this? Oh, yeah. This is the same thing as saying I have this blob multiplied by itself b of those blobs. Look at the blob. It's its own blob. Blob to the b is blob times blob times blob, blah, 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 times blob. And there's b of those blobs. Now, since everything on this baseline is x's multiplications, we can drop the parentheses. I'm not going to write all that out. It's just going to be a bunch of x's multiplied together. How many x's in each blob? A. How many blobs of those do we have? B. That sounds like multiplication. We have b blobs. Each blob is worth a x's. That's where the shortcut comes in. X to the a times b. Can always go back to the definition. Okay, here's a thought. Let's say we have some sort of product on the inside of parentheses, and we raise that to some exponent. Now we're not working with multiple different types of exponents. Now we're working with multiple different types of bases raised to the same exponent. This shortcut is x to the a, y to the a. This is not the distributive property. Even though it kind of looks like it, we're kind of taking a and putting it towards each of the things on the inside that kind of looks like the distributive property, but it's not. That is a completely well-defined property that links addition and multiplication. It kind of looks like it, but it's not. Don't call it the distributive property. Call it power of a product. I think that's what it's called. Power of the product. These properties have very boring names and they can all sound very similar. So I try not to recall property names unless they're like bombastic, like the distributive property. Let's prove this. X times y to the a, by definition, is the same thing as multiplying x times y by itself, and there's a of these blobs. X times y, variables next to each other, is multiplication, and then all of those parentheses, I probably didn't even need to write the times in between, I just kind of did that for emphasis. Everything's being multiplied together here. So I can rewrite this as x, y, x, y, and that pattern repeats, x, y. It's all being multiplied together. But due to the commutative property of multiplication, I can rearrange all of these x's and y's. And just a reminder, there were a of these x's over here, so there were still a x's this way, so there should still be a amount of x's there, which means, back to the definition, we have x being multiplied by itself a times, and then we also have y multiplied by itself a times. Boom. If I put the little box there, that means my proof is done. I learned it in college. It's a formality. All of these exponent rules work with variables and constants as well. We just use variables because they could mean anything, even well-defined positions on the number line. So, for instance, I have a quick example here. By the shortcut we just learned, power of a product, I guess, 4 to the third x to the third, which means we have 64x to the third. Another thing is that the power of a product also works for fractions. So if we have a over b to the x, that's the same thing as saying a to the x over b to the x. And a quick proof for that, this itself is a product. And also, if we have a fraction raised to the negative first power, you can either do the rule I just explained, like that, or you can just reciprocate the entire fraction like this. Over here you can see that the a would be sent to the bottom and the b would be sent to the top anyway.